Alright, draft a physics video. Yeah, so a little bit more on inertia actually, but it has to do with the whole magnetism and the function of the electrons and the protons and how atoms are held together and all that kind of stuff. So it has a lot to do with this, which I've been over before. But let's say that this field of quanta that just fills the universe, these little bits, these little momentum balls, or spheres, or frisbees, or however you want to look at it, balls of energy, they're quanta, they're little discrete bits, complete little things, indestructible, they move the speed of light, and they make all the forces, including light, gravity, and magnetism, all made out of this stuff. So it comes in two varieties of polarization. You could say it much like a frisbee, this way or this way, and that's really all there is, because the other two ways are the same thing. And there could be a third that accounts for neutrons, but I don't think there are. I think neutrons are just bipoles. But anyway, so you have these, the theory goes for this kinetic interaction stuff that when you have an interaction between two of the same polarization, there's nothing to see here. It looks like nothing crashed into each other. Even the head-on collision, yeah, you can see it as a reflection, or you can just see it as going right through, but nothing changes. It's, if something was going straight and it hits something, it's still going straight and nothing changes. So it's when things of different polarization collide that something happens. Say red goes into a blue, then there's a red reflection and a blue reflection, and likewise if red or blue goes into a red or blue perpendicularly, they end up changing their direction, or you could see it as changing their polarization. I think for the sake of this conversation, we're going to go with change of direction. Just because yeah, that's what's on my mind. So what has occurred to me is that the electron is a bit of a sneaky bit. So we'll draw them as blue. And the idea is they have an orientation. I mean, they exist in 3 dimensions. So they have a substance in all 3 dimensions, and in a sense, if they're not moving, that means they have an equal amount in every direction. Now, if they are moving, maybe you could just draw the lines a little bit differently and kind of imply that there's more stuff in that direction than there is in the backward direction. And that might be one way of visualizing it. So what's really happening, I think, I had to come up with, I had hundreds and thousands of days of drawings of this kind of crap, trying to figure out how to get all these arrows to add up to something. And it occurred to me that the problem was I was trying to give electrons momentum, sustainable momentum. And the trick is they don't have it. I didn't really think about it, but if electrons could be shot without losing their velocity, then we'd have guns that could shoot electrons. I mean, not guns that shoot electrons a specific distance to a target that has a charge, but I mean actually shoot them some distance. And we could even communicate with them, or we could kill each other with them, or all kinds of things with them. But the point is they don't maintain their velocity. They do feel the drag of the force, and so they just don't. They don't have perpetual velocity, or they don't maintain any kind of velocity. So they're either accelerating or decelerating. They really aren't in any other kind of state. They don't get to just stay moving right along. You don't get them up to 60 miles an hour and they just keep going 60 miles an hour, because the field will kill that velocity. So unless you create a special field for them to travel in, one that creates a frictionless environment, they'll get consumed. Their velocity will get consumed. And so this was a kind of an important realization that material momentum or velocity is a function of the constituents of matter. So you really have to have the proton and the electron in relationship to each other and in force relationship to each other to create what ends up being velocity in a direction for atoms. So atoms can have velocity, but the nuclear bits can't, because atoms have some capacity to create a closed system, a system where what goes in doesn't get out, and electrons really can't. So there's two elements to this. All right, so to really understand, so the electrons would be understood as a thing, like I said, with all this directionality in it, and but it can be dominated or not. It can have a static condition, and it prefers the static condition in the sense that the field will kind of oblige it to be static. And the proton is in a similar condition. So you have these two things with a different polarization. So one's made out of blue polarization, one's made out of red polarization. Kind of consolidated. No other little bits. So if I was to represent the electron as a thing with an orientation, and these are just, let's say these are directions, so just so you can understand what I'm talking about. Alright, so the field has the same amount of blue as it, I could just run and make a whole bunch of blues and then a few reds here. It doesn't have to be the same amount, because it's really the idea is is that this interaction, the head-on collision, is basically what holds these things together. So in the field of gravity, you have a mixture of these two polarizations, and the reds the blues are what's reactive to the proton, and the reds are what's reactive to the electron. And reactive means it'll give it velocity, or it'll stop it from moving. It's the friction force. So the blue ones are invisible to the electron, and the red ones are invisible to the proton. And so the only real players for the proton are the blues, saying it another way, and the only ones that are players for the electron are the reds. And the trick is the neat part. Well, anyway, so the blue arrows, you can, if you could think of an electron as the bits inside of it. I'm not going to go into this part too extensively, but as I'm thinking of it, these things are different because they are compressed. So in a sense, you could just think that the quanta are kind of stuck to each other, and what they have is it's a stream of them with a directionality, and so basically they go until they hit some of these reds, come in here, turn and create the reflection, and the reflection bounces them back, and they bounce back, and they bounce back. So they're basically just bouncing back between the field energy, okay, coming from both sides. And as long as the field energy is balanced, then they'll just go back and forth, and everything will be fine. No problems. And so when they gain velocity, what's happening is they're gaining some blues in this direction. They're getting longer this way and shorter in some other direction, this way, or even the tangents, the perpendicular directions. I'll get into that. And you can sort of see that if there was more arrows going this way than going the opposite way, that this would tend to move into this field. And likewise, if I made these perpendicular elements shorter and shorter, then this movement would be more and more dramatic. So I think that's all you need to know for that part of it. So just to understand that the field pressure of these red arrows is basically what holds the electron together. So as long as there's red arrows in the field, there's an inevitability that a blue will hit it and it'll bounce back, and so it just really can't get out of here unless there's a special kind of circumstance. Alright, so what you're really talking about is just conversions. So you have basically some element inside of here would be like a. Alright, well, let's draw it as this diagram just for clarity. And so say I have two of these things, an electron that's, let's say, balanced, and so it has it's not moving, and then I have one that is moving, so it has a longer, one end is longer than the other, and then it has these tangents. So the trick is that it's tending to want to move in this direction. Say a force pushed it and it's moving in this direction. And what's going to happen is there's certainly the whatever reds that are in the field it's going to be colliding with, and those are going to slow it down just through head-on collisions. So you can figure that's going to be happening as it goes towards anything in the field. It's just going to tend to get worn down by just hitting red arrows. So that's one friction point, is just there's going to be more red arrows ahead of it than behind it. The ones coming from behind won't be able to catch up as quickly. I mean, the electron doesn't move anywhere near as fast as the speed of light, so the ones coming from behind certainly can catch it, but it just means there's going to be less hitting from the back than there are going to be hitting from the front, and that's going to convert the blue, the extra blue here, into longer blue this way, and so this would balance that line and slow the electron down. But the other factor is that all the perpendicular reds that are coming in from this side are going to tend to have a likelihood to hit this more than this. This is a shorter line than this line, so more of them are going to hit this one. And when they hit this one, what happens is this reaction over here. So in essence, the red arrow converts from one going this way to one going this way, and the blue arrow turns into one of these perpendiculars. So one of the perpendiculars gets a little longer. So something comes in this way, the blue gets bigger this way, the red goes out this way. Right, because it hit this, and so this gets shorter, so this goes shorter by a notch, and the other arm gets longer by a notch. It basically converts this into one of these. Now this one's longer, so any red energy coming in perpendicular from here, let's draw it as red, Gary, is now going to be more likely to hit this than this, which means that it's going to send more reds out this way, and it's going to put the blue arrow back on the other dimension, like this one. And so it's this constant battle between any imbalance in there. These red arrows are going to tend to want to kill. So as it's gaining acceleration, that is, as you're adding force in this direction. Now, whether you could do that with extra blue is a tricky question. Yeah, well, I'll have to think about that. But anyway, so let's just say you add you in the most aggressive way would be to sit there and you add force, red arrows coming in this way. They're obviously going to hit the perpendiculars, and they'll change perpendiculars into more blue, and that's how you'll gain acceleration. And as you're gaining that acceleration, you're going to lose, since these reds are coming in this way, the reds are going to get lost perpendicular, and so that's EMF. So when you're accelerating electrons, you're creating an EMF perpendicular. When you're decelerating them, that is, when these are coming in sideways, or when a red comes in here and reflects, all the red energy, or the EMF, is ahead of the electron. So it's sending more red ahead of it. Now you can sort of understand that if there's more reds going this way than going behind it, because this line is longer, that means if there's another electron, those reds are going to hit it, do the same thing to it, and force it to gain an acceleration in the same direction that this one was accelerating. So that's basically the repulsive force between two electrons. Now if I put them in proximity to, let's just draw a new picture over here. So here we have we have the electron, and say I'm going to take an electron next to a proton, and you can see that it'll have the opposite effect in that there has to be something to, you know, create the initial connection to each other. Something has to move, obviously, for things to become acquainted, so to speak. So as an accelerating electron comes into the purview of a proton, it's going to be doing, again, this tangential conversion here, and anything coming this way, of course, will be converting that, but we won't count that. And this will be the major stuff here, is that more of the reds coming from the perpendicular will end up going this way as force, as this line is converted into longer lines this way and perhaps in the perpendicular. So as you can see, so there's more red coming towards this proton. Now, based on the fact that the same is same, the red is irrelevant to the proton, so it's like nothing coming at it. So it just goes straight through it. And so that absence of force means that the you know, what you converted, which is you killed blues and made them go sideways, you know, converted them going this way, you know, you convert them to going the opposite way or to one of the tangential arms, and by doing that you absorb some blues. So essentially now the field pressure, the normal blue pressure out here, is going to be greater than the blue pressure here, and so this proton is going to move this way, and it has the same rules of its internal structure, so I guess I might as well draw that. So once it starts to gain acceleration, it's got the exact opposite problem of blues coming in from the perpendicular, and it's going to end up creating blue going out this way, and the blues are transparent to the electron to go straight through it. So now it essentially has more pressure behind it than it does in front of it, because there's no reflection. See, any red that goes this way is going to rebound off of the electron. So that's another source of red here, is that all the reds hitting the blue will rebound right back at the proton and just go right through it, and that's a conversion of a blue again. So anything coming this way converts this way or to the negative direction, which means there's an absence of blue pressure coming at the proton, and it's producing extra blue, which is irrelevant to this, and as it's producing, it's releasing these reds. So as these come in here, they are let go as blues, and the red, okay, is extended, is converted into here or into this direction. So the red ends up going somewhere, not forward. So there's no red, therefore you can't move the electron. The absence of red means the electron's not going to be moved away, and therefore it's going to tend to push in. So that's the attractive force. So anyway, this is a little bit I mean, I just, like I said, I just realized today that I don't have to account for a sustainable velocity in these particles, and therefore this will work in terms of they're just constantly at any time they get an imbalance in them, the imbalance is going to be destroyed by the field, and the consequence of that destruction is that they create more energy in the direction they were going, which will affect the thing they're heading towards, in the sense of either go right straight through it because it's the same color, or cause the other body to move away. And that's essentially the mechanism that keeps protons and electrons in their relationship of attractive and repulsive to each other. And so yeah, this is big, I think, in terms of, I can start to model things now that I have this. This is really kind of the key equation, and it's, and it goes back to this, which is sort of irritating because I've been doing this for months. This is the key, I kept saying, and but I couldn't make it happen if the thing gained an actual velocity. So you have to just think of electrons and protons constantly just accelerating, that is, force pushing them, and then decelerating and creating force ahead of them. So they're just constantly, they're never in a state of velocity. They're just in a state of acceleration or deceleration. They have no steady state of velocity. And it sort of makes sense when you think about how it would almost be too perpetual motion-y to imagine them without without some mechanism that retards the imbalance. And so what really creates the imbalance is the arrangement of the proton and the electron. So I would argue that something in atoms, in material bodies, it really is going to be about the fact that whatever the alignment of the protons and the electrons are inside of a structure is going to have more to do with, it can be very complex, like two atoms can be facing each other with another atom in this way. So, oops, I keep missing the balance. So you can end up with all kinds of polarizations, as you can see, and that would create all kinds of field dynamics. But that's really the orientation. So when they're in this orientation, they tend to probably move in a direction. So there'll be a direction that's consistent with the orientation. And in matter, these orientations are in a sense balanced, and the more you have to imbalance them to give matter actual velocity. So when your body is moved fast, the atoms have to rearrange in terms of either the distance between these particles or in terms of their arrangement overall. It might just be the distance. As the distance is greater, it creates more force imbalance, in the sense that this atom will tend to want to move in that direction. So if I brought these closer together, you could argue that there would be a tendency for this is a proton, to move in that direction more aggressively. But see, it's field locked, so even though it has a tendency or desire to move, it can only move by expressing force, and that force gets rewound into the whole system. So when you have matter, what you can essentially have is you can have a system where the force, because it keeps leaking out perpendicularly, it can essentially go in circles. And once you trap it, then you have some hope of shaping it in a direction. Something like that, but I'll get to that eventually. I just wanted to get this works, and of course this will work for magnetism. It's basically the whole point of magnetism is going to be the shape. Magnetism, I think, quite obviously is atoms lined up in this manner. So so it's red and then blue and then red and blue, and they're off center, they're staggered. in terms of, well, maybe they're just straight out staggered. Yeah, no, I think they'd have to have, the force would have to be balanced, so yeah, they're staggered. Oops, that was blue, and this was red here. So there would always be the right distance between the constituent parts and such. And yeah, so what that ends up doing is it creates, when you keep doing that, this kind of a matrix will create a likelihood of not a very good drawing, of likelihood of when something comes in, it's going to end up coming out polarized the opposite way. So because of this happening, it constantly is converting one polarization into the other, and so and the two poles are doing that conversely, which means on the inside they're constantly switching blue and red arrows, so this one can keep feeding out blues and this one can keep feeding out reds. So this one keeps feeding blues to this one keeps feeding red to this one converts into all blues, this one converts into all reds. So it's a really interesting filter, but that's the nature of magnetism. It's just the precise arrangement of the elements being vibrated, and all it is a vibration. You're just talking about an acceleration, deceleration, acceleration, deceleration. Well, deceleration, they accelerate, they decelerate, then they accelerate, then they decelerate, then they accelerate. When I do accelerate, it's the same as my decelerate happens as I'm stopping, and so you're not really seeing it, but it accelerates and then decelerates, then accelerates, then decelerates. So that's, and so when it's accelerating, the force is coming out perpendicular. When it's decelerating, the force is coming out forward. And so it's on the deceleration that a magnet probably produces, well, that's the direction. It produces the force in the direction of the South Pole from the North Pole, and then on the acceleration it produces the perpendicular magnetic field. So anyway, I think that's probably enough for this edition, but yeah, I'm not going to say it's a eureka moment, but it's it's a good one, because I was really struggling. I mean, I can't tell you. I mean, I got pages and pages and pages of drawings of trying to isolate the arrows and not have black things crashing into black things. That was the biggest problem. It kept looking like things of the same polarization should be attractive, and that's not supposed to happen. So that was a real problem. Alright, so yeah, just to add this to gravity, just so there's no confusion. Gravity is mixed, and so what's happening with gravity is obviously the red bits are moving the electrons, the blue bits are moving the protons. So that's how gravity's being blocked. So gravity's essentially two forces. One force acts on protons, the other force acts on electrons, and that's how gravity affects them. And so as they're, I mean, kind of obviously, I think you can sort of understand that as energy as these elements are absorbed in terms of converted into a perpendicular direction, that's the same thing as the piece disappearing from the perspective of something else. So you can sort of understand that if you were a positive body and this blue force came and the blue force left this way, it's kind of obvious to something over here, okay, that this piece of blue force didn't get here. It went that way. So, and if this was red, it got converted into a red essentially. Well, red goes right straight through. So, that's kind of the effect. And so the effect would be that this is going to move forward. And so gravity is doing both that to protons and electrons, and creating electron shadow and proton shadow. And those two shadows are affecting the planets and all that kind of stuff. So it works out the same way, because they're so segregated. Only blue arrows affect red, and only red arrows affect blue. So it's like there's only one force, but it's really two separate forms of gravity, or you can separate if you wanted to, but the way it functions, it'll all end up being the same. It's just that the blues go straight through blue and the reds go straight through red. Alright, that's probably enough now. So, yeah, I'm feeling good about it. I'll probably do a video. I got a couple of links from somebody, and a couple of them show the magnetic waves really well in a graphic, and I was just thinking of that for the two-slit description, just because it's a nice visual. And so I'm going to do some more work on that. But the more you look at it, the more you think about it, it just makes sense. As the slits get narrower and narrower, the field lines straighten out in between, and it just all makes sense. So anyway, enough. And so till next time and such. Probably should do a comment video also, but I think I'll just put this as one of the formal videos. So till next time. Well, you could read this stuff some more. Yeah. So the thing for me to add here is that velocity does not really apply to electrons and protons. So they really don't. See, that's where my misunderstanding was. I was trying to make them velocities, velocitable, and they're not. The atoms can have velocity, but the fundamental nuclear particles can't maintain velocity. Only force can have velocity, that is tons, photon, graviton, magneton. I don't know about quarks and stuff. The interesting about quarks is that there are 3 of them, and it is kind of interesting that, I never end the video, that, this idea of 3 dimensions would be kind of good for up, down, and strange, in terms of quarks. So, anyway, that'll be all, I think. So, yeah, so just, I have to kill all these velocities. Yeah, 4 of them in there. Yeah, just acceleration and deceleration. Acceleration creates perpendicular force. Deceleration creates forward force. So, I think that ties it up. So, until next time, and such.